Welcome back to the course Basics of Mechanical Engineering 2, where we are discussing the manufacturing sciences here, manufacturing processes here. The first part, Basics of Mechanical Engineering 1, discussed about the basics of engineering, which included the theory of machines, strength of materials, etc. Here in this week, we are discussing metal forming. In the last week, you have seen certain metal forming basics and you have seen the processes. I will again walk you through a tutorial session on metal forming, where we will just review the various relations that we saw in metal forming processes such as forging, rolling, extrusion, etc. And we will try to see certain problem statements that how do you design the radius, the size and determine the time, etc. for the different processes which are in metal forming. Just to recall forming mechanism, as metal is deformed, its strength increases due to strain hardening. Flow stress is defined as the instantaneous value of stress required to continue deforming the material. So, this is YF, that is flow stress, which is taken in megapascal. This is equal to K times epsilon power n. This is there to keep the material flowing. It is the yield strength of the metal as a function of strain, which can be expressed as this relation. So, yield strength as a function of strain, it is expressed, except some cases generally forming force is analyzed on the basis of average flow stress and strains. If I say average flow stress, this is YF bar, which is average flow stress. It is from this point to this point. This is the average YF bar. So, it is given by the expression K times epsilon power n by 1 plus n, where YF bar is average flow stress and epsilon is maximum strain value during the deformation process, and n is the strain hardening exponent. It is the average value of stress over the strain curve from the beginning of the strain to the final, that is the maximum value that occurs during deformation. Let me come directly to a problem statement. It is given that during a tension test, the tensile strength was found to be 340 megapascal. It was recorded at 30% elongation. Find the value of strain hardening exponent n and strength coefficient K. Here it is given that 30% of elongation is there, which means engineering strain is given, which is equal to 30%, which means E is equal to 0.3, and we know true strain epsilon is equal to log of 1 plus E. This is natural log. So, to calculate it, this is log of 1 plus 0.3. It is log of 1.3. This is equal to 0.262. This is the value of epsilon, that is a true strain. Now, they are asking the strain hardening exponent and the strength coefficient. So, at ultimate tensile strength, that is UTS, n is equal to epsilon. Now, if I say true stress, this is sigma T is equal to sigma times, that is the tensile strength that was found here, 1 plus E. This is equal to 340 into 1 plus 0.3 which turns out to be 442 megapascals. To understand about the stress strain curve, about the universal tensile testing machine or ultimate tensile strength, or anything about maybe Young's modulus, please refer the course Basic of Mechanical Engineering 1. So here we have calculated 442 megapascal as my true stress. Now this stress is equal to K times epsilon per n, which means 442 is equal to K times epsilon is 0.262 taken from here, this per n, because n is equal to epsilon, this per 0.262, which gives me the value of K as 627.8 megapascal. This is a general problem statement about the metal forming stress strain system. Let me now come to one of the metal forming processes, that is extrusion. Extrusion is a compression process in which the work metal is forced to flow through a die opening to produce a desired cross sectional shape. Extrusion is generally used to create long parts that have uniform cross section. That means there is a die is di plus e. Generally it is said it is die di plus e. Die is two-dimensional and E here is for extrusion. Whatever pipes you see, it is discussed already, those are generally extruded. So if you see bullets, etc., those are all extruded. So two-dimensional die is there. Nowadays the word die is also used for the mold. It is three-dimensional is also being used, but generally it was invented or it was put as a word die because two-dimensional cross section is used to come. There is a ram that pushes the material and this is the extrusion that has come as output. So just to come to the extrusion analysis, assuming both billet and extrudate are round in cross section, there is a ratio known as extrusion ratio. Rx is equal to A naught by AF. A naught is the inlet area, AF is the cross section area of extruded, that is the outlet area, and Rx is our extrusion ratio. True strain and extrusion under ideal deformation occurs with no friction and no redundant work. No further work is required. It is diameter given, initial diameter and final diameter, ram pressure, total length of the billet that is there given as an input, and what is the length output that could be calculated through volume. So ram pressure could be calculated under ideal deformation. The ram pressure is required to extrude the billet through die hole. It is given by P is equal to YF bar log of RE. Here RE could be put as A naught by AF, and also we can put as YF is equal to K epsilon per N by 1 by N that we saw in the metal forming mechanism. So these relations we will use in solving the problem statements coming up. The actual pressure of extrusion will be greater than in ideal case. Why is this greater? Because there is always a friction between billet die and the container wall. This is discussed already again. The actual pressure is higher because there is a friction between billet die and the container wall, etc. Ram pressure to perform indirect extrusion based on Johnson extrusion strain formula is given by P is equal to YF bar into epsilon x, that is the average flow stress times the strain. This is the ram pressure in extrusion. Ram pressure in direct extrusion, you can see the difference between direct and indirect extrusion. Generally for direct extrusion the pressure is higher. In direct extrusion due to friction, it is given here, the ram pressure is greater than the indirect extrusion. P is equal to y bar into the sum of epsilon and the ratio of length by the diameter, where this is an additional pressure. This is additional pressure. I have length of the billet that is remaining to be extruded. D naught is the original diameter of the billet. Ram force in indirect or direct extrusion is given by force is equal to pressure into area. Area is the initial area of the billet. Power required to carry out the extrusion operation, P is equal to force into velocity, where V is ram velocity, and force is calculated from here. It is equal to pressure into area. The shape of the initial pressure build up depends on the diangle. Higher diangles cause steeper pressure buildups. This was all a review of the things that we already have covered in the previous lectures. Let me now come to a problem statement where it is given a cylindrical billet of 40 millimeter diameter and 100 millimeter length, which means my D naught is 40 millimeters and my length is 100 millimeter. This is reduced by backward extrusion to a 15 millimeter diameter. My DF, that is final diameter, is 15 millimeters. If the Johnson equation has B is equal to 1.5 and strength coefficient A as 0.8 of material, 750 megapascal strain hardening coefficient N as 0.15, determine the extrusion ratio, the true strain, extrusion strain and ram force. So, we have been given the initial dia, the final dia as certain coefficients. For instance, K is given here. K is equal to 750 megapascal. We have been given N is equal to 0.15. Also, value of B and A, these coefficients are given, where A is equal to 0.8 and B is equal to 1.5. So, this is a backward extrusion case where, for instance, this is a container and here I have a material and there is a ram which is letting the extrudate coming out. I will put it here. This is my material inside. That is coming out. It has been given the diameter as 40 mm. This diameter DF is equal to 15 mm and length is given 100 mm. This is L is equal to 100 mm. And this ram is a solid body. So, this is backward extrusion as it is given. So, to calculate the final length, because we have been given the final diameter, the initial diameter, and we can just compare the overall volume, that is the volume equation or the continuity equation, we can equate that the volume on both the sides is same, which means pi by 4 the initial square into the initial length is equal to pi by 4 the final square into the final length. Now, to put the values here, this pi by 4 is cancelled on both the sides. I got it as 40 square into initial length, that is 100, is equal to 15 square into final length. This gives me the final length as 711.11 millimeters. Now extrusion ratio is to be calculated. For this, let me first calculate extrusion strain. So part 3, extrusion strain this is equal to change in length over original length. So this is E is equal to length final minus length initial by the length initial, which is equal to 711.11 minus 100 by 100. This is equal to 6.11. This is extrusion strain. Now this part is done. Now because we have calculated the extrusion strain, let me now come to true strain. To find true strain, this is equal to epsilon, which is equal to natural log of 1 plus E, and this is equal to natural log of 1 plus 6.11, that is natural log of 7.11. This is equal to 1.96. This is true strain. That means part 2 and 3 are covered. Next, I can find the extrusion ratio using the ratio of the areas. Extrusion ratio. This is R, which is equal to ratio of the areas. It is equal to A naught by AF. And this could be simply put as pi by 4 D naught square into L naught by pi by 4 dF square by LF. Now you can calculate it. I will just write the answer. This value comes down to 7.11 extrusion ratio. Then comes the last part, that is asked ram force. To calculate the ram force, I need to find the value of the average flow stress, that is YF bar. So this is equal to K epsilon bar N by N plus 1, which is equal to 750 into 1.96 bar N, that is 0.15 by 0.15 plus 1. This value comes down to 721 megapascals. This is also denoted by sigma naught. Now sigma D, which will give me the ram force later, this is equal to sigma naught, that is the flow strength, and the coefficients A plus B log Rx. This is equal to 721 into value of A is given 0.8, value of B is 1.5. 0.8 plus 1.5 into log of 7.11. This value turns out to be 2698.16 megapascal. Now ram force is equal to the stress or the ram pressure into the area on which this pressure is applied. Because it is a backward extrusion, I would have to put the area as pi by 4 the difference between the diameters, the initial square minus the final square. So if we put down all the values, this value comes out to be 2.9 meganewton. This is my ram force. So just using the relations which were given in the previous lectures, I have calculated the 4 unknowns, that is extrusion ratio, true strain, the extrusion strain and ram force. Okay, this was one example of extrusion. Let me take another example which I will try to discuss in drawing. Let me just go through the theory of drawing once. In case of drawing of a cup shaped part, C is clearance, that is here, dB is blank diameter, dP is punch diameter, RD is corner radius, RP is punch corner radius, F is drawing force and FH is holding force. Clearance in drawing is about 10% greater than the stock thickness, that is C is kept as 1.1 times of T. This you already seen. So this is a plate that is drawn into a cup. This plate in technical terms is known as blank. So this is the drawn cup. Here we find a ratio called as drawing ratio. This is defined as the ratio between the blank diameter and the punch diameter. Greater the ratio, more severe is the drawing operation, which means if a bigger blank is there, the drawing would be more deep, it will be more severe if blank diameter is higher. If punch diameter is higher, blank is smaller, this ratio would be smaller. Limiting value of dr as less than equal to 2 depends upon the punch and die corner radii, friction conditions, draw depth and quality of sheet metal like ductility, degree of directionality or strength properties in the metal, etc. Here also reduction is there. Reduction R in deep drawing is equal to dB minus dP, that is blank diameter minus punch diameter over the blank diameter. This is the value of reduction, which is typically less than equal to 0.5. Thickness to diameter ratio, that is T by dB. Thickness ratio should be greater than 1%. As T by dB decreases, the tendency for wrinkling increases. Because if thickness is very less, it just looks like to be a very thin sheet or just like a paper that will wrinkle if you try to draw it. So this thickness ratio is generally greater than 1%. Now to calculate the forces, certain relations such as F is equal to pi times of dP into T into the ultimate tensile stress times the difference between the ratio of the billet and punch diameters and 0.7, that is maximum drawing force, and holding force is 0.015 times the yield strength into pi times this relation. Here generally FH is equal to F by 3, that is approximate holding force is 1/3 of the drawing force. Using these relations, let us try to see a problem statement. Here it is given a cylindrical cup without flange is to be drawn from a 2 mm thick sheet, which means I have been given a blank. If I try to draw it in a 2-dimensional, here this thickness T, its diameter is D, T is equal to 2 millimeters, that is given. Diameter, let us see what it is given. A cup shall have 15 millimeter diameter and 40 millimeter height. A cup is to be drawn from here which should be 15 millimeters in diameter. This is 15 millimeter and height should be 40 millimeters. Reduction ratio in the first and subsequent draws may not exceed 40% and 15% respectively. Determine the blank size and number of draws necessary. That means dB is to be determined. And we have been given the thickness of the blank, we have been given the final diameter and height, that is 15 millimeters and 40 millimeters. Let me try to solve this. A blank diameter can be calculated by equating the surface area, assuming the variation in thickness is insignificant. To equate the surface areas, I can say pi by 4 of the dB square, that is the surface area of the blank. This is equal to the surface area of cup. Surface area of cup would be pi by 4. I just put it as the cup diameter as small d, plus the surface area of the cylinder, that is the outside area of the cup, that is pi dh. So this is blank and this is cup. So this gives me pi by 4 dB square is equal to pi by 4, this value of d is 15 millimeters, plus pi into d into h. D is 15 and h is 40. And here we can calculate the value of dB as 51.23 millimeters. So overall ratio, if I need to calculate, ratio, it is overall, that is equal to the blank diameter by the final diameter, that is punch diameter generally of this size only, which is equal to 51.23 by 15. This is equal to around 3.41. The question is blank size and number of draws necessary. Now here I will use an arithmetic progression. The ratio 3.41, it is not in one draw. In the question it is given, it is asking the number of draws necessary. Number of draws necessary means in the first draw the diameter have been reduced somewhat, then in the second draw, in the third draw, in the fourth draw, whatever the number of draws would happen, finally it is reduced by 3.41 times, that is from 51.23 to 15 millimeters it is reduced. So to use this as a progression, let me put the formula here. Let me say d1 is equal to diameter of cup after first draw, and this also becomes my blank diameter for second draw. Before the first draw it is complete sheet. After the first draw the diameter is reduced. That becomes my output dia of the first draw, but this becomes the input dia of the second draw. That means this becomes my blank diameter of the second draw. Subsequently, we can keep putting d2 as diameter of the cup after the second draw, which is my blank diameter of the third draw, and so on. Here I can put it as the blank diameter by d1 into the second draw, that is blank diameter by d2, that is d1 by d2. This is first draw, this is second draw, and so on up to the number of draws is equal to 3.41. Now let me come to the question statement once again. It says the reduction in the first and the subsequent draws may not exceed 40% and 15% respectively, which means 40% reduction is there. If I try to put it, this gives me in the first draw d1 is equal to, with 40% reduction, that is 1 minus 0.4 of the original blank diameter. This is equal to 0.6 of the original blank diameter. And in the subsequent draws it says it cannot be more than 15%, which means D2 is equal to 1 minus 0.15 into D1, that is 0.85 into D1. Putting these values here, because there are n minus 1 stages, draws or n minus 1 stages, I will put it as a geometric progression 1 by 0.6 into 1 by 0.85 per n minus 1 is equal to 3.41. This is very interesting problem. Here I will put it as 1 by 0.85 per n minus 1 is equal to 3.41 into 0.6, which is 2.049. Now taking log or natural log, I will put it as n minus 1 log of 1 by 0.85 is equal to log of 2.049. This gives me the value of n as 5.41. Now n is 5.41, that is number of draws would be 5.41, which means more than 5 draws would be taken to get the final shape, which means number of draws which has to be a whole number, that is 6 number of draws. Now question was find the size of the blank, where we have gotten the size of the blank, the diameter as this, and the number of draws which is 6. And this was a problem on drawing. So with this solution, I will take a break. I have discussed forming mechanism, extrusion and drawing in this part of the tutorial. Next part of the tutorial on forming I will continue, where I will discuss further metal forming processes such as rolling and so on. Thank you.